Well, thank you very much for asking me to come and talk about the Eastern Mediterranean today. And really enjoyed Andrew's introductory speech and the discussion of how all these countries in the Eastern Mediterranean work. And I'm going to set my stall out here by filling this cup half full. I don't want any misunderstandings about what I'm about here, because I strongly believe that the Levant has only started to give its reward, and it will keep giving, and I want to show you why that is. So, the area I'm going to be talking about is the eastern part. This is of the Mediterranean, the areas around Lebanon and Israel and Egypt and Cyprus. So, first up, we've had two talks about the perception of exploration and the perception of the future of the oil industry in the Eastern Mediterranean so far this morning, and we've identified a whole series of issues that are really above ground issues with many of the countries in this area. So security issues in Libya and security issues in Syria. There's also commercial issues with Israel, and we know that the operators there have had some difficulty moving to commercialise the big Leviathan field, but I think they're there now, and they are moving forward with that. So these commercial issues, as indeed all above-ground issues, can be solved. And the other perception that we have picked up in the industry is that the Nile Delta is over. It's old news. The only gas to be found in the Nile Delta is deep and expensive, and, you know, don't trouble your little heads about it, is the kind of thing that you're told. And then, very last point to note is a couple of poor well results offshore Cyprus in 2015, and it leads to a picture that the Eastern Mediterranean is not a very interesting place at all. There must be other places to look around the world. But then it all changed, and the game changer was the discovery of Zohr, which was this gas discovery out here. We've had it mentioned a couple of times today, and I'm going to show you some seismic around Zohr and introduce you to some Zorettes, some Zohr lookalikes that they have in the area. I've also shown here the data set that Spectrum has in this area, so it will be the basis of the talk, will reflect that. But the key thing about Zohr is that it not only changes the geopolitics of the area, because somebody's just magically found 30 TCF down the back of the sofa with the crumbs and the bits of pizza, but not only has that happened, but it also changes the geological story quite dramatically. And so I'm going to develop that theme as well as I go down. But let's start just a little further to the east. Let's start with offshore Israel. So offshore Israel, what everybody knows is that it's a gas basin. Well, it is sort of so far, but is it always going to be a gas basin? The whole story there started with the Tamar discovery in 2009, and this was quite a landmark type of well to be drilling. It's in 1,500 metres of water, and it's a gas discovery. And it was brought on stream in 3 years. So I was so hoping that Stephen was going to offer to eat his hat if he and I did the same in the Nile Delta. And the reason it was brought on stream in 3 years, despite it being gas, despite it being 1,500 metres of water, which in 2009 was still deep, despite all that, the way it was brought on was that it was tied back to a facility that had ullage, the Mari B platform that had ullage in shallower water. It was tied back with a 75-kilometre tieback. And this is exactly what's going to happen to Zohr. So you don't have to have a 15-year development cycle. You can bring these discoveries on in 3 years. And fingers crossed that he and I managed to do it. If I had a hat, I would offer to eat it, but I don't. So, lucky me. So what was followed by Tamar was followed by a whole series of discoveries as Noble drilled up the, they're not quite lookalikes, but the other big features offshore Israel and at the edge of Cyprus with the Aphrodite discovery. And in total now, there's something between 40 and perhaps 50 TCF of gas has been discovered in this play fairway. So the industry perception is that this is a gas basin, and at the eastern Mediterranean, if what you're doing now is you're looking for gas, probably dry gas, probably biogenic gas. Or is it? The other things that we know about the Levant Basin is that the reservoirs, the early Miocene reservoirs that have been explored for in Tamar and Leviathan, these are locally derived sands that have just fallen off the Arabian plate. Another thing we know, and that the structures that we'll find there are really quite complicated structures tectonically. Now, the problem with complicated structures is that you need lots of wells to develop these fields, and if it's in deep water and you're spending $150 million a well to do, for each development well, you need 30 development wells. That's a lot of money into development. If the structures were simple and if the sands were simply distributed within those structures, you would develop these fields with perhaps 2 or 3 wells. So the fact that it's complex structures is a real problem perhaps for the eastern Mediterranean. So all these things point towards the Eastern Med being kind of an awkward place to be, but I don't think any of that is true. So now I'm going to work through those issues one by one and suggest that there may be another way to look at this. So this is a seismic line that runs south on the left to north through the Tamar discovery, which is offshore Israel, into the northern Levant Basin, which is in offshore Lebanon. And the reservoir in Tamar is this one here. If you look very, very carefully, you can see a kind of flattish event here. And this was the thing that made Tamar so attractive, was that there was a flat spot that you could identify on 3D seismic, as it turned out, that mapped out over about 100 square kilometres, which reduced the risk, shall we say, on drilling it. It was still risky because no one knew what the sand was going to be, but it reduced the risk, the fact you could see that flat spot. Well, the thing is that this reservoir here is a couple of 100 metres thick, beautiful sands, stacked turbidite sands, a couple of 100 metres thick, and if we follow this reflector as it comes into the northern Levant Basin, it runs into here. This is the early Miocene sequence in the northern Levant Basin, and you can see it's probably 4 times as thick. It's about 1 kilometre or so of early Miocene section with that wormy acoustic impedance contrast that tells you it's full of clastics. So in terms of the reservoir thickness, as we move to the north, it's certainly more significant. And then if you think perhaps why this should be, it relates us back to a story that actually takes us back to the drainage pattern of the Nile Delta during the Cretaceous. So that's where this story starts. During the Cretaceous, all these hinterlands up here were all draining towards the west and draining out through the Niger Delta. Then at the end of the Cretaceous, these rivers were captured by a rift system that was heading north, and so for the first time we started to get sands coming into the basin. And in the early part of the tertiary, the sands being drawn into the basin, which was the proto-Nile Delta, were actually dragged across to the northeast by contrarite currents that were running from the east to the west. And the reason this was happening was that from the Cretaceous, when the Tethys Ocean was open to the east, this seaway here was still open in the earliest part of the tertiary, and so that was connecting through into the Persian Gulf. But then this closed, and it closed at the end of the Miocene, the late Miocene. Now, once we closed it by the northward movement of the Arabian Plate, we closed the eastern end of the Med, then we could dry it out and we could create the Messinian salinity crisis that we're all quite familiar with, and the deposition of the Messinian salt. But until that point, it was open to the east. And the other thing that happens, of course, when you actually close this ocean at the end of the Miocene is that there's no big contrarite which is dragging the sands from the Nile Delta across to the east. And so the Nile Delta starts to develop like a normal Nile Delta. It just develops to the north and to the east and to the west. So it just develops as as a normal Nile Delta. So it's in the drainage pattern of the development pattern of the Nile Delta that we start our story. And if we look now at the basin offshore Lebanon and offshore Israel, the model that we have is that locally derived sands may have come off that Arabian plate margin, but they're very small and very locally derived. But the main deposition has come from the Nile Delta across the southern Levant basin, which is where these two blobs are located, and then fallen into this great big hole in the ground, which is the northern Levant basin. And they basically just fill it up. So the source of the sand is from the Nile, not from the Arabian plate, and the depositional mechanism is for large, very, very large turbidite systems, stacked turbidite systems, just filling up the northern Levant basin. And here's an illustration of how that might work, so that you have a platform area, which is now the southern Levant basin, which is where Tamar is, and in local little half-graben, you deposit the Tamar sands. They're small amounts of sands that are captured, but most of the sand bypasses the southern Levant basin and just falls plop into the northern Levant basin. One of the lines of evidence that tells you that the sands are not derived from locally derived sediments has come from some work that was published by Bertoni and Cartwright in 2006, and they'd looked at the margin of Israel here. They looked at that in some detail, and they mapped out the Afik Canyon. Well, the Afik Canyon is cutting into this section in here, which is early Miocene. That's the early Miocene equivalent of the sands offshore, so that the early Miocene sands couldn't have come from the Afik Canyon because it has to cut its way into that shelf. And the other thing that we know about the region, as of the last few months anyway, the other thing we know is that in the early Miocene, we were growing a series of big carbonate reefs just here. And if the Nile Delta was coming to the north and then dropping its sands to the north, or at least prograding to the north, then those sands would have killed the development of the big reefs that we're now exploring in the Zor and the Zor lookalikes. Because plastics kill reef, we know that. So in order to avoid that, we have to take the sands that are coming from the Proto-Nile and we take them to the east and dump them in the northern Levant basin, well away from Zor. So what we did was we've mapped out the early Miocene section, and we mapped the isopack of the early Miocene out, and the blue area there is the kilometre or more section of early Miocene, and the reds and the yellows and the oranges are the thinner section in the southern Levant basin, which is the basin that's been explored to date. And what you notice is that you very rapidly, as you come across the basin here, you very rapidly pinch out of this early Miocene sequence. It very, very rapidly pinches out. And that's quite important because as these sands come piling across the southern Levant basin, they just drop into the northern Levant basin. They don't migrate off to the west and crawl around Cyprus. They don't go anywhere near Cyprus. They just fall into the northern Levant basin. And this might account for a couple of well results that were drilled recently. Two wells drilled by ENI, the Onasagoras well and the Amethusa well, which is drilled here. And these are drilled on the west side of the northern Levant basin, away from where the sands end up. And when we look at the seismic on those wells, this is an east-west line going through Amethusa, which is looking at the pinch-out play here up against the Eratosthenes seamount. This is the early Miocene sand that we can correlate back to Tamar and to Leviathan. So this is the early Miocene sand unit, and here you can see the bright acoustic reflectivity. As you come across to the west, that reflectivity just disappears because you're up on the shelf. There's no reason why a turbidite is going to go and sit up on the edge of the shelf of this basin. All the sands end up in the bottom of the basin. It's like when you drop the soap in the bath. The soap ends up in the bottom of the bath. It doesn't end up where the taps are. You know, it's not rocket science. So here, one would suspect that the problem with this well is perhaps the lack of sand in that pinch-out play. As is always the case when you're drilling a pinch-out play, sometimes the sand pitches out, which I suspect is what's happened now. We look at the other well that was drilled, the Onosagoras well, which seemed to be drilled on a valid structure, but again, here's the early Miocene sand sequence in here, and this is where it's 1 kilometre thick. This is where it's stuffed full of sand. But where this well was drilled up on the site in Cyprus is where this whole early Miocene unit is really just about pinched out on an early structure. So it's again, you know, it's not unsurprising that that well was unsuccessful, if it was unsuccessful due to the lack of sand, which of course I don't know. So either of those two wells, actually, they don't really throw that much of a bad light on the exploration that you might find to the east in offshore Lebanon and in the northern Levant Basin. They're kind of specific wells to the northern margin of the early Miocene fan system, and they're basically drilled where you wouldn't expect to find sands. But in the centre of the basin, this is what we expect to find: 1 kilometre or so of thick early Miocene sands in relatively straightforward structures sitting in the middle of the basin. So that is the main play offshore Lebanon, in my opinion. The main play is these early Miocene sands that we can explore for, not looking for stratigraphic plays, but for looking for nice, simple structural plays. And anybody who's seen seismic over Tamar will understand the geometry of what I'm showing there, because it's the same sort of geometry, rather simple type of structure. Gotcha. Okay, so we got an idea that there may be an argument for there being a decent reservoir in the northern Levant Basin, based on the offset wells and the understanding of where these sands might have come from. But what about the hydrocarbon charge story? Now, the thing about Tamar, Leviathan, and so forth, all of the early Miocene sands there have discovered dry gas. So the understanding is that these are biogenic gas discoveries. Does that mean to say that in the Eastern Mediterranean there's no possibility of finding an oil source? Well, the normal way we go about finding an oil source is to understand what the geology of the basin is and then do some basin modelling. But in the Eastern Mediterranean, what we seem to have said is, well, everyone seems to find dry gas, that's probably all you're going to find. It's not as scientific as actually looking at where the source rocks might be and doing some modelling. Now, in this particular line, which is, again, the same line from Tamar up into the north, we have this section underneath it. So this is 1 kilometre of sand, and sitting underneath it we have an Oligocene section, and we have an Eocene section. It's well known in this area that the Eocene has some source rocks in it, but there's not much known about the Oligocene because it doesn't outcrop onshore Lebanon. However, the Oligocene in the Nile Delta is 1 or 2% organic carbon, and it's well known to be a contributor to the at least the deeper discoveries that are made in the Nile Delta. So it's an established source rock, and it's probably the first one that you would model. And when we do a basin model of this horizon here, the Oligocene in here, based on our ability to map all this on 2D data, when we do that basin modelling, what we find is that in the south, in southern Levant Basin, where Tamar and so forth is, the Oligocene is not mature for generation of anything, not mature for generation of oil, not mature for generation of gas. And so it's a slowly subsiding basin and relatively low geotherm, and it gets biological activity generates the gas. So that's why Tamar's stuffed full of gas. But when you fall off into the northern Levant Basin, you bury the Oligocene source rock that much deeper, and you cook it, and it becomes oil generative. And we can see that from about the Mycenaean onwards, from about 6 million years onwards, the source rock, the Oligocene source rock that's sitting underneath a kilometre of sand in the northern Levant basin is generating oil, and that oil is going to be migrating into those structures. And it might be that though the reason that we don't see obvious flat spots in offshore Lebanon in the deeper parts of the early Miocene play is just because it's not gas, it's oil. It's an oil play. And then the question becomes, well, just how big could this oil play be? I would say before moving off this slide, although you're quite capable of reading it as I'm wittering away here, but moving off this slide, evidence for there being a working oil system is present in Lebanon. And it comes from a series of oil seeps, natural oil seeps, that you can see on optical seep data. You can also see it on SAR data. And in general, it runs parallel to the coast, quite close to the coast. So this has led the sort of thought process to be that quite near to the coast, there's a working oil system. And so people have looked at Jurassic type of source rock and Jurassic systems working quite close to the coast. But it's not quite how this basin works, because if we take this as being the Oligocene in here, and we start cooking it and generating oil, that oil comes up and then it starts to migrate beneath the Messinian salt layer, which in this area is more or less planar. And so typically the oil will then migrate along the base of the salt and pop out quite close to the coast. So the fact that you see oil close to the coast just means that there's a working oil system in this basin, not that it's only close to the coast you're going to find oil. It's quite important distinction. So what other evidence have we got that there may be an oil system here? So this is the familiar slide that we had before of the discoveries, the dry gas discoveries. Leviathan itself was deepened and the operator started to report the fact they recovered liquids. They pretty soon stopped doing that because I think everyone got the idea it might be an oil basin and get very excited and competitive about offshore Israel. But they did report initially the thermogenic liquids in the deep Leviathan structure. And then they've drilled another structure called Karish. And Karish is located much closer to the border with Lebanon. And at first it looked like just another rather boring gas discovery, just be tied into the other discoveries in the fullness of time. But then, and I have to say it's apocryphally, I don't know this for sure, but then it was reported that Karish was slightly different because it too had recovered liquids. It was a gas condensate. So where does this gas condensate come from? Well, it comes out of the northern Levant basin and it just migrates up dip into the Karish structure. Karish structures itself is quite interesting because this is the Karish well drilled right here, and here's a couple of lines that are close to it. This is the early Miocene section, and it looks like it pinches out as you come up dip onto this structural feature here. So Karish, I think, has got up dip closure, and it tells you where that early Miocene sand has an up dip termination. So that allows us to, looking at the whole basin, mapping this up-dip termination of the early Miocene sands, that allows us to make this map. And this map is our view of where the early Miocene sand onlaps. Now, it may not be exactly right, because in this area, our colleagues, PGS, have 3D seismic data, and they could probably nail down that pinch out better than I can do it on 2D data. But in principle, the early Miocene sand is filling the deeper part of the northern Levant basin, and it's not necessarily gas prone. It could be an oil play in that basin. So here's a bit of a story about a potential oil play that might be working in the northern Levant basin. So how does this affect Karish or Zor? And conversely, how does Zor affect this story? So from what we understand at the moment, the Zor feature here is an early Miocene reef. So it's grown at the same time as the sands, the turbidite sands that form the reservoir in Tamar and form the reservoir in the northern Levant basin coming into the basin. it's an early Miocene reef, and we understand that the gas is a very dry gas. Now, nobody's said that it's a biogenic gas, but the odds are it's the same biogenic gas as you get in Tamar and so forth. So it says something about the deposition rate and the substance rate and the geotherm around the Eratosthenes seamount. So it's a gas story, and it doesn't corroborate an oil story, and I want to be very clear about that. When the discovery was made, of course, because we've got seismic data, well, it's a little bit of an advert, but I mean, Spectrum itself has got 3 million kilometres of 2D data all over the world. So when anything happens, we go and have a scurry through the data and see what we can see for that discovery. And in this area, we have quite a lot of data, predominantly to the north of Zohr. So the first thing we wanted to do is see if we could see Zohr, and we can see Zohr now, although I have to confess I couldn't see it beforehand, and it helps when it's coloured in. But we can see it now, and then of course having got our eye in, so okay, so this fuzzy sort of imaging is not just poor seismic imaging; it's actually the reef part. In the middle, you get a bit more coherence, so that's probably a lagoonal facies, and then you get some more fuzzy reflectivity. So, having got your eye in and suggesting, well, that's probably not just seismic imaging, it might be something else, we went looking around for other features like this. So, this feature, Zohr features 100 square kilometres. So we went looking around. It didn't take us very long to spot this feature, which has got fuzzy reflectivity on either side and then rather coherent reflectivity in the middle. So when I put that on it, you get a sort of Zohr lookalike creature. And this one is not an itty-bitty, almost can't see it, 100 square kilometres. This is a 500 square kilometre carbonate reef, and it's just sitting again on the Eratosthenes seamount, on the edges of it, and covered by Messinian salt. And these are probably the key play elements that we need to think about as we go look for these features. Here's another example, just a little bit further along. Again, I think we've always seen this big knobble sticking there, but we never actually knew what it was. So now I think we've got an idea that these are early Miocene carbonate buildups. And presumably they all have some prospectivity rather similar to Zohr. So if those were predominantly north-south type lines, this is an east to west or west to east line going over the Eratosthenes seamount, which is this guy in here. And this is the northern Levant basin, so you can see Leviathan and Aphrodite with the early Miocene reservoirs in here, and then these big carbonate buildups which actually sit on both sides of the Eratosthenes seamount. The Eratosthenes seamount itself, just if you can just bear me a slight digression, it's really, really cool because even though now it's in like 1,500 metres of water, just shy of 1,500 metres of water, at the time of the Messinian, they were depositing paleosols there. So the Eratosthenes seamount was exposed at the time of the Messinian salinity crisis. So it strikes me you do this two ways. One is that you either pull all the water out of the Mediterranean, which I like, but not everybody likes, so that you completely desiccate the Mediterranean. And the other way to do it is to very rapidly, since over the last 6 million years, you very rapidly subside that whole seamount, and probably due to the fact that it's been pushed under Cyprus at some point, and that sort of tectonic forcing of this subsidence. But the interesting thing is that this exposure may relate to the carbonate buildups that are all around the Eratosthenes seamount, and presumably they were exposed, maybe they developed a karstic porosity at that time, and maybe that's why these carbonate buildups are going to work. And I'm sure in the audience today, we've all drilled carbonate buildups which didn't work for one reason. Well, okay, I've done it, but I don't know if everybody's done it. And this may be one of the things that will make this play repeatable, and I think that's going to be important, as was mentioned by Stephen. It's just one well in one carbonate bank we have to make this repeatable to add the significant reserves. The Eratosthenes seamount, which is located here, is supposed to sit on attenuated continental crust, and that the oceanic crust is basically to the west and generates the Herodotus basin and so forth. That's the conventional model. I don't know if we actually really know any of that. I don't know if we actually know what the Eratosthenes seamount is made of. It may be just a bit of folded oceanic crust for all I know. All I know is it's sticking up in the early Miocene, and we were growing reefs around it, and that's probably all we need to know at this stage. So if we take another line here that runs around the seamount, you can see numerous of the zorettes just sort of growing around there. So there's huge potential in that area to the north. My understanding is that there are more of these carbonate buildups offshore Egypt, not all of them in the ENI acreage as well. So I think that this part of the world has huge potential that will roll on from Zor because of this repeatability. So very lastly, then I'm just going to very briefly talk about structures. So I'm going to migrate back to the east and fall into the northern Levant basin, because from the basis of this 2D line, you see all these faults in here, the basis of the 2D line, it would seem to justify the model that the northern Levant basin is just shattered by faults, and that it's hopeless finding anything in the northern Levant basin because there's so many faults that you need lots of wells to develop it, it's deep water, yada yada, you can't make it commercial. Just not true. So when we compare this map here, this is a map of some of the structures we were just looking at. The thing is, that was a really, really long line that has been squashed up, so no wonder it looks busy. These structures here of the same size as Tamar, so here's Tamar, and they're the same size, and to be honest, they're less faulted than Tamar is. And if you look at Leviathan, you know, if I had £1 for every fault on Leviathan, I'd quite a few pounds. Because here it is here. I mean, it's not shattered, but it's just lots and lots of faults. Now, Leviathan is saved because it's a ton of sand, so across these faults, it's unlikely you're going to get fault sealing. But this is a kilometre of sand too in the northern Levant basin. So these are going to be very simple structures, very easy to develop, and they won't need too many wells. And my guess is that they will be developed extremely quickly in the ENI aspiration, or in the noble, yeah, we've done that, model, where they just do subsea tiebacks and tie these things straight back to the shore. Of course, it won't be as easy as that if it really is oil, because these will be billion-barrel fields that you'll have to develop properly, and it will take more time, but you'll probably more value. So a couple of examples of the structures in the northern Levant basin. This is a surface within the Miocene unit, and it shows one of the wonderful things about this basin, and that is that the faults that are virtually east-west faults here are all more or less parallel to each other. So you've got these east-west faults across here, and these are crossed by large fold structures which push through the structure itself. Now, the formation of these piano key faults, these vertical faults, there's still a bit of debate on it, but the model I particularly like is the one that's developed from field examples in the canyonlands of Utah. Can we negotiate on that? Right. Yeah, okay. No more than 5 minutes. Probably. Yeah, okay. Right. Counting now. Okay. Hold on to your hats then, as we go into the explanation of these faults, because it's so easy peasy. What you have is a detachment surface below this sequence of fairly brittle material, and these faults just root straight into that detachment surface. In this case, in Utah, it's salt. So you know it's mobile, you know it's a detachment surface. You see exactly the same faults in the northern Levant basin, but there's no salt underneath it. There's something else. There's the thick Oligocene section. Now, if that was a thick Oligocene shale and it was just hard, brittle shale, these faults would not detach into that shale. They would go straight through it into the Cretaceous, but they don't. They stop in the Oligocene shale. The reason they do that is that the Oligocene is the source rock, and it's generating hydrocarbons, and it's actually viscous, so it's deforming as if it was a mobile unit. And what this creates is a kilometre of sand sitting over a Oligocene source rock, big structures, big individual structures. So each of these structures here is, well, the equivalent of about a billion barrel field, if you want to put it in that order of magnitude, or 7 to 9 TCF of gas if it turns out to be gas. But what's really cool about the middle of the Northern Levant Basin is that these structures all connect up, and they connect up into this monstrous ridge in the middle of the basin. And so this potentially gives you the repeatability thing, in that you can drill Cronus structure here, and it's got to significantly reduce the risk on all of these features because they're all within the same closure. So this is what will happen when Northern Levant is actually explored, the offshore Lebanon, is that we'll have one successful well, which can be developed really quickly, but we'll just have that repeatability. Sounds a bit like an explorer getting ahead of himself, but this is exactly what's happened just to the south, offshore Israel, where Noble just drilled well after well after well and then found 50 TCF. So in the actual detail of the structures, we've mapped them at all sorts of levels of detail. The level of complexity is no more complex than Tamar, so it won't be any less developable than Tamar. So we go to the Northern Levant, ask 3 questions again. Is it just a biogenic gas play in the Northern Levant Basin? No. It's probably an oil play as well. Does offshore Israel have the thickest, best quality reservoirs in the Levant Basin? No. Go to the Northern Levant Basin, you'll find them 3 or 4 times as thick. And are the best structures in South Lebanon? No. The simpler structures are in Northern Levant Basin. So then, last slide. Yay! There you go. As Andy Warhol has showed, you can rush art. So, last slide. This is what we found to date. Something like 100 TCF in the Nile Delta, whether it be in the Pliocene, in the Miocene, and these super deep wells that are being drilled, or the Abamadi. So something like 100 TCF there, and something like 50 TCF offshore Israel. Following Zohr, there's got to be 50 TCF in the Zohr analogues that wrap around the Eratosthenes seamount. And on our evaluation in Northern Levant Basin, there's probably another 50 TCF at all. And if you just go by closology alone, you can see that there's some potential truth in this. And this shows you what will keep coming out of the Eastern Mediterranean, and I would heartily encourage you all to explore it if you can. Thank you.
Thank you.